All right, welcome to lesson 9.03. We're going to begin looking at volume today, and we're going to be applying the definite integral to solve problems that involve volume. Okay, so let's take a look at a volume problem, and in trying to solve it, we will develop the intuition necessary to compute volumes of any kind. So the region R, shown below, is the area bounded by the two curves and the y-axis. The region R is the base of a three-dimensional solid where each cross-section, think slice, is a square that is perpendicular to the x-axis. Our goal is to find the volume of the solid. Okay, so here's what I'm going to do. I'm going to draw, to the best of my ability, this three-dimensional solid, and I want you to take a look at the drawing and attempt, using what we know about computing area and how the integral can serve to sum all these infinitesimally small things together, to find the volume on your own. So let's take a look at what this solid should look like. Okay, so it's clear that I'm no artist, but what you can see here is the green curve, the red curve, and the y-axis. And the base, of course, of our figure is that area here. And each of these yellow cross sections is a square. And so this is the three-dimensional solid. You can imagine it being filled in, of course. And what I want you to do is spend about 5 minutes trying to compute this volume. And even if you think you've really failed in doing it mathematically, at least come up with an idea for how you might compute this volume. Alright, so let's see how close you came. What we're going to do is sort of go step by step. So complete each of these steps on your own, then press play and we'll take a look at them together and we'll actually find the volume of this solid. So first, draw a single cross section of the solid and label the dimensions. So cross section is, you can think of as a slice of this solid, and I want you to actually draw it on the graph here. Okay, so here's our typical cross section, and notice I've drawn it in a random place. It doesn't matter where I draw it along my base. And it's a square, so all the side lengths are equal. And since the bottom side length is simply the distance between the curve y equals 10 and the curve y equals x squared plus 1, we have an expression for the dimension of our square. In other words, that the side length of our square is simply 10 minus x squared plus 1. And this should be pretty simple based on all the work we've done with computing the area of regions like this. Alright, so now that we have the dimensions of our square, write an expression for the area of this square cross-section. It should be in terms of x. Okay, this is quite simple. We're dealing with a square here, and we know the area of a square is simply the side length squared. And since we have an expression for the side length of our cross-section, we know that the area of these cross-sections is just going to be that side length squared. So now we know the area of any cross-section. Okay, now here comes the big move. What would be the thickness of these cross sections if we had infinitely many of them, and we used infinitely many of them to represent the volume of this solid here? So if you think of the volume of this solid as being the summation, or the adding up of all these infinitely small cross sections with these tiny little thicknesses, the thickness would become dx because we have infinitely many of them. So delta x becomes dx when we take the limit as n approaches infinity. And so what we can see here is that each of these cross sections really has an infinitesimally small volume, which is simply the area multiplied by dx, right? Volume is simply area being extended in another dimension. And so if we take this paper-thin slice and we give it a thickness of dx, what we have is an infinitesimally small volume. So we can represent the volume of each of these cross-sections as an infinitesimally small volume where we take the area and multiply it by the thickness of this cross-section dx. So now write a definite integral to represent the volume of this solid. Remember that the definite integral is just going to allow us to add up all of these infinitesimally small volumes that we have an expression for. Okay, so this should be pretty simple. Notice all we're going to do is add up these infinitesimally small volumes at every single x value between 0 and 3, since that is the interval over which our base exists. And so we know that the area of each of these cross sections is simply 9 minus x squared squared. Notice I've just distributed my negative sign here and combine some like terms. And I can compute this either by squaring it out and taking the antiderivative by hand, or simply using my calculator. And doing so gives us a volume of 129.6 cubic units. And there we have computed the volume of this solid. So let's go ahead and give ourselves a nice definition and clarify some of the things that might show up when we're computing these volume problems. Alright, so computing or calculating volume. The volume of a solid from x equals a to x equals b that has known cross sections with an area given by an integrable function, a of x, is simply the integral of a from a to b. In other words, this equation here. So the volume of a solid is the integral from a to b of a of x dx. Go ahead and copy this down, and there's a couple of things that I want to mention. All right, the first is these cross sections. You want to think of a cross section of a solid as being those slices, and each of those slices has an area, right? We think of it as being a paper thin slice. And so what happens is when you take the area of those slices and then you're going to multiply it by the thickness, a of x dx. And so when you have an area multiplied by some value that extends it in another dimension, in other words, gives it a thickness or a depth, that gives us a volume. And so what we're adding together infinitely many times over this interval are these infinitely small volumes. And of course, that is going to give us the volume of our overall solid. So you want to make sure that you're thinking about taking the area of those slices or those cross sections and then multiplying it by the thickness, dx, as I've written right here, of area times thickness. And that, of course, is giving us the volume of the cross section. And we add those up infinitely many times. Okay, so there are actually two situations in which we can apply the definition that we just described for computing the volume of a solid. And we're going to tackle the first situation today. We actually saw an example of it in the discovery problem. So if we are given a region for the base, the type of cross-section that we're going to use, and the orientation of the cross-sections. Notice they were perpendicular to the x-axis. They could also be perpendicular to the y-axis. We'll see an example of that. Here's what we want to do. We want to sketch the base, if that hasn't already been done. We want to sketch a cross-section and identify its dimensions. Notice that the dimensions should be in terms of a variable, x in most cases. We want to construct a function for the area of any cross-section. So this will require us knowing some basic areas, area functions, like the area of a square is side times side, or side squared. And identify the limits of integration. These limits of integration are going to be basically the region of our base. So where does our base go from A to B, wherever that happens to be. And then we're going to just set up an integral, as we have here in our definition, and compute it, or evaluate it, to find the volume in units cubed. All right, let's go ahead and take a look at another example. All right, so here we go. Find the volume of a solid whose base is the semicircle y equals square root of 9 minus x squared, with cross sections that are equilateral triangles perpendicular to the x-axis. So notice we've been given all of those three criteria. We have a region for the base, we have the type of cross section, equilateral triangles, and we know that they are perpendicular to the x-axis. So go ahead and try following all of those steps that we've just gone through and that we did in the discovery problem, and then go ahead and press play and we'll take a look at the solution together. Alright, so here I've sketched my base and I have drawn a cross section here, and this is an equilateral triangle, so all the side lengths are equal. And so remember, the dimensions of a triangle are its base and its height. So I need to know the length of the base and the length of the height. The length of the base, obviously, is just going to be the y value of our curve, so the square root of 9 minus x squared. Now, the height requires a little bit of thinking if you don't remember the equation. Here we have a height that runs perpendicular to the base. And so if you consider this triangle here, this is a right angle, this is a 60-degree angle, because we had an equilateral triangle, and that makes this a 30-degree angle. And so you can just go back to your unit circle here to remember this. So if you had a 60-degree angle, which is pi over 3 radians, and you consider the fact that your hypotenuse was 1, then your x value, your cosine value, is 1/2, and your sine value is root 3 over 2. What that means is that the value of your height for a 30, 60, 90 triangle is going to be square root of 3 over 2 times the size of your hypotenuse, since our hypotenuse in our unit circle is 1. So our height here is going to be root 3 over 2 times the square root of 9 minus x squared. All right, now that we have the dimensions of our cross-section, we now need a function that will give us the area of our cross-section anywhere in our region here. And of course, we know the area of a triangle is simply base times height times 1/2, or 1/2 base times height. And while this looks a little hairy at first, notice there's a lot of simplification that can go on here with our coefficients, as well as squaring the two square roots. So let's go ahead and simplify that. And now we're ready to make sure we know our limits of integration. We're going to go from -3 to +3, and since the thickness of each of these cross sections is simply dx, we can go ahead and take our area multiplied by these infinitesimally small thicknesses, dx, and take the definite integral from -3 to 3, and that will give us this volume. And so here that is. Notice I'm literally just applying the definition we just stated, and when I input my area function, I can factor out this coefficient here. So I have square root of 3 over 4 times the integral from -3 to 3 of 9 minus x squared dx. This is actually pretty easy to evaluate using the fundamental theorem of calculus. We can take the antiderivative here, or you can use your calculator. I'll show you the antiderivative method here. There that is here. I end up with 9 times the square root of 3 units cubed. If you were to approximate that, that's about 15.588 units cubed. All right, let's take a look at one more example. All right, so here we want to find the volume of a solid whose base is the region R shown below, and whose cross sections are semicircles perpendicular to the y-axis. So this is a different orientation for your cross sections, but it's nothing that you can't handle. Go through it, find your volume, and then go ahead and press play, and we'll look at the solution together. All right, so this here is a little tricky simply because we're looking at semicircles that are perpendicular to the y-axis here. And so when I look at the dimensions, I know I need the radius. And so I know the radius is half the diameter. And I know the diameter here is the distance between the x value of the blue curve and the x value of the red curve. I have both of these equations solved for y, so I can easily find the y value, but I need the x values, and I'm going to be integrating along the y-axis because all of these different semicircles are going to be defined by the y value that we're at. So I need to solve these two equations for x so that I can write my expression for the radius length of my cross sections. Alright, so that seems scary at first, but it's really not too bad. The x-coordinate of my red curve is given by the y value minus 1 over 5, and the x-coordinate of my blue curve is simply the natural log of y. Remember, I can take the natural log of both sides, and that can solve for my exponent here, in this case x. So the radius of my semicircle is going to be half the diameter, and the diameter is the x value of the blue curve minus the x value of the red curve. So it's 1/2 times natural log of y minus 1 over 5. And now I can write the area function for my semicircle pretty easily. Alright, so the area of a semicircle is going to be 1/2 pi r squared, so it's half the area of a full circle, and I know my radius length is this expression here, so it's going to be 1/2 pi times our expression for the radius squared. And now I know that the thickness of each of these cross sections is dy, since I'm going to be splitting my y-axis up into infinitely many pieces. And therefore I can write my volume as a definite integral in terms of y, and my limits of integration are going to be from 1, where they intersect here on the y-axis, all the way up to 14.32, where the intersection point is up here. And there we have it. No need to go ahead and rewrite the area function that we already have. We've already written it here, so when we write a of y, we know what we're referring to. And this is a function best integrated in the calculator, and in doing so I get 1.779 units cubed. What you want to take away from this is that when our cross sections are perpendicular to the y-axis, we're going to differentiate with respect to y. So you want to add that into your notes. And of course, if they are perpendicular to the x-axis, then we are going to differentiate along the x-axis, or with respect to x. All right, at this point, go ahead and move on to the homework 9.03.